So how many of you guys have seen Kalman filter and like its derivation or its usage? Well then, I mean, you can go. No, okay. So there are many derivations for Kalman filter and a lot of different implementations, a lot of different interpretations. So I'll show you two of them, well, one step and the two step. And then I will try to cover a little bit of UKF. So, and if I have time at the end, I'll probably say something about how you can use this Kalman filter for linear regression that you would be doing a lot in the system identification and parameter estimation. It's just like posing the problem differently and using Kalman filter. Okay, so what is the state estimation problem? So you're given, you have a system, and usually we're going to talk about linear system in the beginning. So it's xk plus 1 equals axk plus buk plus wk, and its output is cx of k plus v of k. So you have this linear system. It's driven by the external input u, which you assume that you know, and this noise signal w, which you don't know. Maybe you know the statistics of the noise signal. And you have the output or the measurements from the linear system, which are also corrupted by the by this noise. Usually this is called measurement noise. And this is called process noise. Okay, so the goal is to, so problem is that if you're given y of k, given like a sequence of y of k and u of k and abcd, I'm not considering d. I mean, you can, but that doesn't really make it. Well, you know what, let me just write it. Plus v of k. So that this is, yeah. Okay. So given ABCD, estimate x. So at each step construct x. Find x hat of k. Okay. So if the dimensions of y and x are same, then that problem is trivial, right? I mean, assuming some matrices are full rank, you can just compute x from the measurement of y. Compute, not estimate. Estimation means you're doing something else. Computation means just you have a closed form formula, right? So it's only useful when you have very few sensors, very few measurements. Like you have one measurement or two measurement, and your state is like 8 numbers. So you want to get an 8-dimensional vector from a 2-dimensional measurement. An example of which is like you want to measure temperature somewhere and a pressure somewhere, and you want to estimate the state of global atmosphere, right? Like hurricanes and those things. You want to predict those things. So those, that's why state estimation problem is useful. So let's do an example. So if you have like a double integrator, like a rigid body, okay, you can write it like that. And if you write its equation, if you write this equation in the state space form, it ends up being x1 dot x2 dot. Actually, I'm just going to do the state space and the discretization in just one step. It's not that difficult. This is going to be 1 delta t, 0, 1, x1, x2, plus 0, well, I think delta t, I guess. U plus noise, you know, assume that there's noise, and then you're measuring the velocity. No, you're measuring the position. So if you're measuring the position, then that's your output, and then it's also corrupted. Okay, so we want to estimate x1 hat and x2 hat at k. Okay, so x1 is the position and x2 is the velocity. So how would you do that? If you have only the first state, so 1, 0 is going to pick up the first state. If you want the first, if you have the measurement of first state, how would you find x2 hat? You can just differentiate it, right? Yeah, but the problem is this guy, right? You have noise there, and you don't want to differentiate signals which have noise. You may have like high frequency content in the noise, and that may mess up your estimates of the velocity. So what you do is you just set up an observer. So you guys probably know about observers from your linear system stores. So you set up the observer, which is just a copy of the system. So it's going to be the same. I'll call this A, B, C, A x hat, where x hat is this guy, plus B U K, plus K times your output error. Okay, and output error is what you measure and what you compute, right? And then y hat of K is equal to C x hat of K. Okay, will this work? Does this say that x hat is going, if this is your actual system and this is running in your computer, what are the chances that this is going to converge, this x hat is going to converge to x, right? Certain properties have to be satisfied by that matrix K, gain K, so that x hat converges to x. Okay, so to see how you choose that gain K, we define the error K. We've seen this many times. X of K minus x hat of K. Some people do x hat of K minus x of K, but we'll do x minus x hat. So if you define error like that, then you see that E evolves like this. So you just take this equation and subtract, no, you take this equation and subtract that equation. So you get x k plus 1 minus x hat k plus 1, which would be A E of k. So this, the input term would be cancelled. This would be there, plus W of k. And then this would end up being minus k. And y is Cx plus V. And this guy is Cx hat. Oh, let me write it. Right, so this would be minus k C E of k and minus kV, I guess. So this whole thing ends up being A minus kc E of k plus W minus kV. Okay, and step. So that's the big K, not the time step, and that's the small k, which denotes the time step. Okay, so, well, yeah, now you have this noise term which is driving your error system, but just ignore that. And under what condition is this matrix, or E, going to go to 0? That's what we want, right? When states converge, when your estimates converge to your true states, error is going to go to 0, right? So you see that if this matrix, you can put all the poles of, no, all the eigenvalues of this matrix inside the unit circle, then your error will go to 0. Okay. When is that possible?
It's observable.
What's that?
When it's observable?
Yeah, when AC is observable, right? If AC is observable, then you can choose, then we can choose big K such that A minus KC is asymptotically stable, right? Asymptotically stable means that its eigenvalues are inside the unit circle. Okay. Question. What if the eigenvalues of A were already inside the unit circle? Then you don't even need the output error injection, right? Then you don't even need any K. You can just start the model anywhere you want with the same input. The states will converge automatically, right? So you don't even need to come to the class then. Okay, so where is this system evolving? E. You know, this is the real system. It's happening physically. This is in your computer. Where is this? What's that?
It's in the computer as well.
No, you don't implement it. It's nowhere. just analysis, right? You're just looking at it to see what may be happening, right? Error system is nowhere. It's just, we're just analyzing it. Okay, so the Kalman filter is basically just a statistically optimized way of computing this gain k. So we look at the statistics of the process noise and the measurement noise to optimize that gain k in some sense. Okay, so you just write some cost function, minimize it, and the minimizer of that cost function is going to give you that matrix k. You don't have to use that k. You can use any k which makes A minus kc asymptotically stable and you're good to go. But Kalman filter is just optimal in some sense. Okay, so I will show you the one-step Kalman filter derivation. It's not done in one step. The derivation has a lot of steps. Implementation is one step. And there is a two-step implementation, which I will have to talk about because I want to do UKF. Most useful implementations of Kalman filter, which are basically in nonlinear system, right? So you have ensemble Kalman filter, you have extended Kalman filter, unsended Kalman filter, and a lot of varieties of Kalman filters. They all work with the two-step interpretation, and it's a little bit easier to see, but it's a little more messy in terms of notation. So let me show you the Kalman filter derivation with one-step implementation. Okay, any questions so far? Yes.
What type of noises are those? Are those Gaussian line noise?
No, so far I haven't made any assumption on what these things are. When I do Kalman filter derivation, we'll have certain assumptions on these. That we'll see. Okay, so Kalman filter is, again, it's just an observer. It's of this form, AX hat of k plus BU of k with error injection with this time varying gain matrix k, y of k minus y hat of k, right? Okay, and y hat of k equals cx hat of k. Okay, no noise. You don't inject noise in your filter because you don't know that, right? Oh yeah, this is the one. Okay, now the assumptions that we need to make about the noises. So we assume that the process noise W of k is, well, I mean, we don't need to make the assumption that they are Gaussian. What we really need is the expected value of W is 0. Expected value of V is 0. The covariance of W is, I think Q, right, Q. And covariance of V is R. So that's 1, that's 2. W, V, X, U are all independent. Which means that if you look at the covariance between W and V, that's going to be 0. Covariance between W and X and all those pairs is going to be 0. Is everyone comfortable with the idea of expected values and covariance? If you don't know, then you can just ask me at the end of the class. So these two conditions are also satisfied if, like equivalently, I can say that W is distributed as a Gaussian, right? So you write it like this. And V is also a Gaussian, so 0, R. So that means it's a normally distributed random variable with mean 0 and covariance matrix as Q. Okay, so again, we look at the error. So this is the one-step form because the estimate is obtained in just one step, right? You just have the this equation is not really a physics update, it's not really a data assimilation update, it's both of them at the same time, right? This part is the physics update, and this part is you're correcting your estimate by using the measurement and your computed outputs, right? So this part is usually called the data assimilation part, because you're assimilating the data. Simulation part. And this is the physics update, right? Or the other word is predictor corrector type. So this would be the prediction based on the physics of the system, and that would be the corrector based on the data that you measure. Okay, so next we look at the error. So that's again going to be defined as x of k minus x hat of k, which you can use to write this error dynamics. E of k plus 1 would be x of k plus 1 minus x hat of k plus 1. Then you just substitute all these values back. So you end up getting a minus kc, just like, so this is going to be k of k. E of k plus w of k minus big K of k. Oh, no, it's just v of k. Okay, so this is exactly what we had just a few minutes back. So I'll call this matrix A tilde of k, and this whole thing W tilde of k. Okay, again, the problem is just to find out k, which makes A minus kc or A tilde asymptotically stable. But in addition, we want to choose k of k such that some cost function is minimized. Right? Okay. I'll define one more thing because this would be useful. Z of k is like the output error. It's going to be y of k minus y hat of k. So this ends up becoming C E of k plus V of k. So just doing just using these two equations, this one and that one. I'm not using D, okay? Don't worry about the D. Most systems don't have D. Okay. So what do you think the expected value of this guy is? Expected value of this is 0, expected value of this is 0. This is like, okay, this is a function of k, but we're not talking about across all steps k. At each step k, you have a constant matrix multiplying this signal, okay, and I'm talking about the expected value at that step. So at that step, it's going to be 0. So expected value of this is 0, okay, so that you can see clearly. What about the expected value of the error? Well, you can just take the expected value of this guy. This is all constant at each step. So expected value of this equals this times expected value of this plus 0. So the only solution is that the expected value of that is going to be 0. And similarly, expected value of the output error is also 0. Okay. So this is done. And what about the covariances? So now we have to find the covariances of these three signals because they would be used. Can you guys see this part? Okay. So the covariance of W tilde is, so this is defined as W tilde K, W tilde K transpose. Right, everyone knows this. Yes?
For your Z of K, shouldn't you also be subtracting minus Y hat K at the end?
So Y of K, so this is going to be C X of K plus V of K, right? And then this guy would be minus C X hat of K. So I'm combining C, pulling back C, X of K minus X hat of K, which is E of K, right? Okay, yes?
Could you explain once more why W tilde is 0? The expectation value.
By definition.
Was that
Is that by definition? But anyways,
by definition?
so this is a random variable. That's a random variable. I'm not talking about across the steps. At each step, okay, you fix a step. This is a constant matrix, right? So if you have two random variables, x and y, let's not do x and y. Let's do m and n because I'm using x and y. So am plus bn. It's just the this is a linear operator, right? So I get a expected value of m plus b expected value of n. And the expected value of this guy is 0. Expected value of this guy is 0. So the sum becomes 0. That's the assumption I made, right? So w and v are 0 mean. So that's why the whole expectation becomes 0. Expectation is a linear operator, right? Okay. Okay, so then you find the covariance of that guy. Is everyone okay with this definition? Everyone has seen this, right? So you can work it out. You can substitute the expression of w tilde, which is right there. And then we made assumptions about that the fact that w and v are independent. So anything which contains w times v or v times w is going to be, that covariance is going to be 0. So this ends up being q plus k of k r k of k transpose. Okay, so you can work this out. And I'll most likely post a much better version of notes in the Canvas page. And there I will have like a full derivation of this. Okay, so covariance of E of k. What is that? So that we define as P of k, right? So that's going to be the covariance matrix that we will be propagating. So it will come up. Okay, and last, covariance of Z of k. Again, define it using the same way, and then use this expression. You end up with R plus C P of k, C transpose. Okay? So given again k, you can find the covariance of that guy. Given a matrix P, you can find the covariance of the operator. Yes?
Your P of k is just another variable that you have considered, right?
Yeah, just define it to
Define
that
it,
to be the error covariance. P of k is the error covariance. Okay? So now we look at the propagation of the error covariance. And that we do by, should I erase something? Okay, maybe I'll write there. So I can erase this part, right? Okay. Okay, so P of k plus 1, which was defined, P of k was defined like that, so this is just going to be the covariance of E of k plus 1, which means it is the expected value of E of k plus 1, E of k plus 1 transpose, right? And where is E of k plus 1? Okay, this guy, right? So you can again substitute these values in this expression and use the fact that E and W tilde are independent, so any term which includes both of them is going to be 0. You can write this as A tilde k, P of k, A tilde k transpose plus Q plus K of k R K of k transpose. Okay. So far, we haven't talked about how to get the gain k. So you can choose any k in your estimation model, and then you can compute your error statistics like this. All right, the covariance matrix propagates like that. The output error statistics are given by that equation. So you can compute your error statistics. I mean, they're not optimal, but they're there, right? So we can also substitute A tilde with that expression, like just A minus KC, because that will make it easy to see when I differentiate that. So that ends up being this guy, plus K of K, C, P of K. May have an error. Well, we'll see. C transpose K of K. So this guy and this guy are symmetric. Yep. Okay. And then this guy. Okay, C transpose K of K transpose. Yeah, it's loads of bookkeeping. A transpose, and then the last two terms plus Q plus K of K R K of K transpose. That's just, this step is just bookkeeping. All I did was I replaced A tilde with A minus KC, and then it just expanded everything. And why did I do that? Because I'm going to define the cost function J of K as the trace of the covariance matrix. So at each step, we are trying to minimize the trace of the covariance matrix. So everyone knows what a trace is? Trace is the sum of the diagonal elements, right? And what does the diagonal element of P have? It's going to have stuff like E1 squared plus E2 squared plus E3 squared plus all the way to En squared. Right? Because that's what it is, right? It's expected value of E of K transpose. So on the diagonals, you will have the square. So it's like minimizing the sum of squares, right? Okay, and then it's a very easy step. How do you minimize something? Differentiate it, right? And everything is continuous here, so you can differentiate it. And what are we getting? We're trying to get the K and K matrix, right? So we differentiate it with respect to K and K. And there are rules for differentiating matrices with respect to matrices. Okay, this is scalar or a vector or a matrix? Matrix? Scalar. Trace. That's a matrix. Trace of a matrix is a scalar, right? So I'm differentiating a scalar with respect to not even a vector. It's a matrix, right? It's a very difficult job. Excruciating. Okay, and there are rules to differentiate scalars with respect to matrices and vectors with respect to matrices and whatnot. If you want to know those rules, you can look at his book. You know, he has that big matrix mathematics book. It's somewhere in the department, right? Yeah, he has listed all those rules. So all you end up with, so this one doesn't have any K. This has K. So anything which doesn't have K goes to 0. And whatever you're left with, it's going to be like this. Minus 2A P of K C transpose plus 2K of K C P of K C transpose plus R. So two quadratic terms, right? I have this quadratic term and that quadratic term. I guess that's why I get these two. And this doesn't give anything, this doesn't give anything, and these are linear in K, so these would give me this. And then trace has property that you can transpose it because it's a scalar, so that's why you get the 2 there, okay? And then what do you do to get the gain which minimizes this cost function? That's just going to be the gain which makes this expression 0, right? So that's, where should I write it? Okay. So everyone can read this side and that side? Okay. So gain K of K, which minimizes that cost function, is going to be A B of K C transpose C B of K C transpose plus R inverse. Okay. and that is it. So that's the gain. That's the choice of gain matrix K, which minimizes the trace of your covariance matrix, right? So in that sense, Kalman filter is an optimal observer. Okay, what is the guarantee that this is going to exist? I mean, I took an inverse. It may not exist. Why does it exist? Because, well, our covariance matrix we assume is positive definite, and this guy is also symmetric, so it ends up being positive definite. So sum of two positive definite matrices is a positive definite matrix. So that's why its inverse is going to exist. Okay. Any questions so far?
How are we finding P of K then?
You have K of K.
Yeah.
See, to propagate the covariance matrix, you don't need an optimal gain K, right? Whatever gain K you chose in your filter, you can just keep using that gain K, and that gain will give you the error statistics that you actually have, right? This error statistic propagation is completely independent of what gain you choose. If you choose an optimal gain, you'll get some error statistics evolving in time, right? So if you substitute back these gains in this equation, then you get the optimal error statistics at each step. Okay, any other question? One thing to note is this P matrix, which is really a Riccardi equation, right? P is evolving as per the Riccardi equation. It's completely data independent. Just depends on ABC, your gain K, and how you initialize P, right? Doesn't really care about what data is coming. It doesn't really care about where, it's not going to react to data. Like suddenly your data changes, it's not going to react. It's going to do whatever it's doing, right? There is no injection of any X or Y or anything. This is completely a closed form solution. You can run it separately. You can run it at home, save all the P of I's and K of I's, and then come back and implement that filter, this filter with appropriate values of K. It'll work, right? And there are books on the solution of Riccardi equations, and under certain conditions on ABC, this P matrix converges, right? It may, depending on ABC, it will have some solutions. It may have a unique solution, that it may have many solutions, or it may have no solution. But in this case, when AC is observable, it always has a solution. It has a unique solution. It converges to something. If P converges to something, then K converges to something, right? So have you guys taken 580 linear feedback at Professor Bernstein? So he does LQE there. In LQE, we're just looking for constant gain, right? We are optimizing over infinite horizon, and we assume that K basically converges. So that's it. That's your Kalman filter, one-step Kalman filter. All you do is you initialize P with some value. For that given value of P, you have K. You compute your state estimates, you progress, and then you update your P matrix as per this equation, right? And then just the cycle goes on, right? Any question about the one-step Kalman filter?
Can you explain a little bit the relationship between the R, which is the output, the error variance that's up here in here, K?
This one?
Yeah.
So that's the covariance of your measurements. I erased it. Y of K was CX plus V. It's the error statistics of your measurement, how good your sensors are.
It's that affects the calculation of the K, right?
Yeah, that is used. So that's, in a way, it's saying if you have, okay, so if the covariance is small, if the covariance is small, that means your sensors are very good, right? Small number, inverted, that means K is going to be big, which means you want to put more weightage to your measurements, right? You're more confident here, less confident there, and you're more confident there. So that's what these things, they're basically weighting. It's a weight. It's a weight between physics update and the data assimilation update. So that's how these Q and R matrices work.
And is there any part of the Q's?
Yeah, Q error variance, right? What is it saying, really? P of K is actually usually bounded, lower bounded by Q. You can't drive it below Q. What is it saying? It's saying your state estimate cannot be better than what your actual state error is, right? The X of K equation had that X of K plus 1 was AXK plus BUK plus W. If at each step you're adding or subtracting W, you cannot estimate better than that over a period of time, right? So that's why P is always going to be lower bounded by Q. How do you choose Q and R? Well, you don't choose them. They're given to you, right? That's the system. Whatever system you have, you're going to know what kind of measurements you have, and you're going to know what kind of disturbances there are in the system. So you'll probably have an idea of what Q and R are. But that being said, you don't even need to get them accurate, right? Yeah, your estimator might not be optimal, it might be suboptimal, but it's still working, right? Yes.
I mean, it's more easier to get the idea of what the R is, but for me it's really hard to what the Q will be.
You mean what it should be in practical system?
Yeah. When I try to estimate for a certain physical system,
Okay.
I know what my sensor is, so I can.
Yeah. So you're saying that R is associated with a physical sensor.
Yeah.
What is this associated with? It's associated with nothing. There is no physical meaning to W. It's just that certain processes. Yeah, it's actually a good question. What kind of process would have a Gaussian noise in the state? I don't know. Usually, you'd say, oh, you don't know the dynamics completely. You just model this part. And then this part could be like a bias, or this part could be like colored noise or white noise or Gaussian distributed. So more like an unknown part of the system is usually modeled this way. Stochastic systems, I think in EECS they have stochastic systems. They study a lot of stochastic systems. Not in aerospace we don't study stochastic systems that much. So they probably have, they would have good physical examples of systems where you have this term modeled as a Gaussian noise. Yeah, but I don't know in aerospace what would it be. Okay. Yes.
I don't understand how we can assume that X and U are independent. Because
X and U are independent?
X and U. You said in the assumption X and U are independent. But with the last equation.
Oh yeah, I shouldn't have said that. Yeah, because we don't, okay, so assume that I didn't say it because there is never going to be a term which is going to be a cross multiplication of X and U.
So what would be the right assumption then? It's just
W, V,
and U.
X are independent, and then W, V, and U are also independent. Yeah, I don't think there is any term which involves U and X.
If you look, X is still dependent with W from this last equation. That's the last option you just wrote. X plus 1, X of K plus 1 is a function of W of K, so that's what's disturbing the term.
Well, okay, so W affects X of K plus 1.
Yeah.
But doesn't. W of K does not affect X of K. That's what it means. See, independence is not really an effect like this. What you want to see is that if in a random experiment, if you change W of K, would X of K change? No, X of K is affected by W of K minus 1, not W of K.
Okay.
So independence is a little subtle thing.
Okay.
And a lot of variations exist of Kalman filter, right? You can start assuming that W and V are correlated. In that case, you will have a cross covariance term, and then you will have more correction terms, right? You can start, then there are there are derivations which assume that this W and V are colored. What does colored mean? It just colored means, so independent meant that covariance of W and V is 0, right? Covariance of WV is 0. So you can start assuming that maybe this is given by M. Okay, you can assume that the expected value of W of K, W of K minus 1 transpose is N. So all these variations exist, which would all they would do is add certain equation to the certain term to the P matrix. So a lot of variations exist. You don't want to worry about all those things. Okay, any question about the one-step implementation? Okay, good. So let me start talking about the two-step. And the equations we end up with are going to be exactly the same, but the notation is slightly different, and it may be the notation that you might have seen earlier. Okay, let me erase stuff. Let me erase this stuff. So in the two-step Kalman filter, you have the physics update. And then you have the data assimilation update, or the data assimilation step. Assimilation step. Okay, so what's the difference? I really don't know. I mean, there's one thing that I can point to, but that's pretty much it. So in one step, you are updating the estimate of the state X in just one go, single equation, right? In this two-step method, we have to use a little bit more involved notation. So we'll denote X hat of K, K minus 1, K vertical bar, K minus 1. That's a prior estimate of the state. So that means that that's the estimate of state K given the information till step K minus 1. Right? This is coming from the probability notation. And then X hat of K given K means a posterior estimate of the state. Okay, so that's the estimate of the state when the information till step K has been used. So we get this by the physics update, and then we get this by the data assimilation step. Okay, so similarly we define the covariances. P of K given K minus 1 is defined as the covariance of X of K minus X hat of K given K minus 1. Yeah, there's a lot of opportunities for me to make a mistake here because there's just an infinite number of indices. Covariance of the state, or the error covariance at step K, given all the information till step K, is going to be covariance X of K minus X hat K given step K. Okay? So that's fine. Okay, so let me erase this stuff. So the assumptions are again going to be the same. Okay, so this guy, X hat of K given K minus 1, is obtained by the physics of the system. So that's going to be X plus BUK. Okay, and the next is updated. I'll show you that in a minute. Yeah, so this is horrible notation because then I have time indices in brackets here and subscripts here, but bear with it. Okay, so earlier I was doing k from k plus 1. No, k to k plus 1. Now we are doing k minus 1 to k, right? And it's just because I started writing like that. I mean, you can just translate the whole system from k to k plus 1, but it doesn't really make any difference. Okay. So where did I go? Okay, and then, so this is the first step, and the second step is going to be now you have to use the information at step k to update this. That's going to be this one plus k of k. So this is the data assimilation step. Y of k, that is your measurement. And I think it's going to be y hat of k, where y hat of k is equal to just this guy. See x hat of k, k minus 1. Yep, that is correct. Okay, so that's the first step. Actually, these two are the first step, and that's the second step. You know what? Let me write it. It's okay. That's like 1A. Okay, so you update your state using the physics, and then you again update the state using the available measurements. Okay, do you see any difference between this and the one-step method? I mean, all I did was just break down that long equation in two parts and messed up the notation. Right? Well, the only thing that I see is different, and I really don't know why it is done like that. I've read a bunch of papers about this and a bunch of textbooks. They all do this. See, in the previous one-step equation, x hat at k plus 1 was obtained using x hat of k and y of k, right? So all the information was till step k. In this system, now I'm going from k minus 1 to k, but you can assume that I'm going from k to k plus 1. In that case, the latest update is being performed using the measurement at the latest step. So k and k, right? If this was k plus 1, then this would be k plus 1. So do you see the difference? In the one step, it was x of k plus 1 was being obtained using y of k. In two step, x of k plus 1 is being obtained using y of k plus 1. And I don't know why. I mean, Kalman filter doesn't really care about when the data is being injected. It's very robust to data injection. It's very robust to time shifts and everything. So somehow it just works. Okay, so this is, yes?
So is this difference between the predictor and?
Well, yeah, the previous one step is usually called the predictor because it's predicting the states. And this one is really using all the information available. So this is really called the estimator. So if you see that this equation is always linear, right? Irrespective of your plant or system, this is always going to be a linear combination of your best estimate till k minus 1 and whatever you observed, right? This part could be linear or nonlinear, right? So if it was nonlinear, then you can use different methods to propagate the matrix. So I'll show you how these matrices are being propagated, right? This one is going to be propagated using the physics, and the next one is going to be propagated using the data assimilation step. And that's how you see all this stuff being done in climate science and everything. Yes?
So I think I missed it, but what is 1A again?
Well, this really goes with that. I'm just saying that when you compute this, then you compute this, and then you compute this. I mean, you can't compute this one without y hat of k, right? So this just should go there because there was no space, so I wrote it down there. Okay? So, yeah, it's pretty boring. Okay, so now, what about the P matrices? They have to be propagated. Okay, so P of k given k minus 1. So that's the covariance of this guy, right? And you can expand this x of k is again given by axk plus buk plus w. And then x hat of k minus 1 is given by this equation. When you do all the algebra, you're going to find out that this is a, b, k minus 1, a transpose plus q. Okay? So that's really sort of the error covariance and your process noise being added. So if you add two random variables, their covariances no, let me say it this way. So if you have a random variable ax plus by, and you want the covariance of this, the covariance of this would be, covariance of this guy is going to be a square, covariance of x plus b squared, covariance of y. So if that convinces you, that's good enough. If that doesn't convince you, then I'll post the notes. Then you can read it there. Okay, so that's all that happened. W was multiplied by 1, so nothing, and E, which is P, is the covariance of E, right? So that's multiplied by A, so that's why you get A and A transpose. Okay, so that's the physics update, right? If your system is nonlinear, then this is the equation that changes, right? In extended Kalman filter, you would be linearizing, and then these matrices would be linearized versions. In ensemble, you have ensembles which are going to compute, which you're going to use to compute this guy. So this equation is the one which changes every time, depending on the system. The next equation remains same. That is the propagation of this guy to this guy, P of k given k, because that operation is always linear. Since it's linear, which means it's you're adding two random variables. Its P matrix is again going to be, well, I have a lot of equations. Which one should I give you? X hat, so this guy equals this. You can substitute y of k as c x of k plus v of k. Then you'll have a giant equation, substitute it back here, and that will give you P of k given k equals I minus k c P of k minus 1 I minus k c transpose plus k r k of k transpose. So that's the first step, and that's the second step, right? Physics update and the data simulation update. This is always going to be same. Yes.
So your k underscore k is the same as k parentheses k.
Good point. Yeah, so subscript k is the same as the bracket k. Parentheses k. Okay. Halfway there. Okay, then can you guess what Kalman filter is doing? All it's doing is it's minimizing this guy, trace of this guy, right? So you just expand this. Again, you're going to get quadratic terms and linear terms in k, and just constant terms in k. You differentiate that, and that gives you the K matrix k. So let me just do that quickly. So this is just a bunch of algebra. You can work it out if you don't have anything better to do in your life, or I'll just post the notes. J of k is defined as, again, it's the trace of P of k given information till k, right? So you expand this guy out, and you'll have quadratic terms in k, linear terms in k, and then you differentiate. Okay, this is not time. This is really, it's a function of k, which is a function of time. And then you're differentiating with respect to k of k. So that, again, ends up being minus 2 pk, k minus 1, c transpose, plus 2k of k, c pk, k minus 1, c transpose, plus r. Yep. So that's very similar to what we had earlier, right? And again, the minimizer gain k is the one which makes this 0. So that's going to be, k of k is going to be p, k, k minus 1, c transpose, c, p, k, k minus 1, c transpose, plus r inverse. Okay? And that's the game that you need to use. And if you substitute this gain into 2, it simplifies a lot. It just becomes I minus k of k c, p of k, k minus 1. So yeah, 2-step has a little more nicer looking equations than the 1-step. Okay, any questions so far? So, so in the 1-step, what we the p of k that we were seeing in 1-step is this guy, right? So that's p of k, and this is really x of k, x hat of k, right? We were not seeing this intermediate state estimate and this intermediate p matrix update, right? Otherwise, these two expressions are exactly the same, right? It just has a more explicit form of the internal variables, right? So again, up till this point, you can use any k to propagate your error statistics. This k just gives you an optimized error statistics, right? So that's 2-step Kalman filter. Okay. Any question on this?
So last question is that after you substituting.
So if you substitute this expression of k in this equation, you get this. Just algebra, a lot of algebra.
But we left out one of the k's in that equation on purpose.
Which one?
In p of k given k, we have I minus k of k at c, right? So we didn't substitute this k, right?
Yeah, yeah. So this one, I mean, you can do that, and then it'll be
Just-
bigger expression. It's just that looks nicer in that form. And a lot of data assimilation papers are always going to use the second equation. Oh, I mean the 2-step form. The main reason is that it really splits the process, right? This is the physics update can be linear or nonlinear. So this equation and this equation for nonlinear systems or different variety of Kalman filters would be different. But this equation and this equation are exactly the same all the time. And so is this one, because this is really a statement about this linear combination. We are saying, when is this linear combination optimal in some sense? Right? Okay. So I have 20 more minutes, and I have a lot of nonsense. Okay, so now I'll tell you a little bit about UKF. Yes.
Sorry, before going into that, can you explain like a step by step? Usually there are like a two stuff, like the states and the P.
Yeah, like how you implement this?
Yeah, when you try
Okay,
like
good question. So when you're writing your code, you'll have, let's say you have xk minus 1, xk minus 1, and pk minus 1, k minus 1. Your goal is to use the data and the estimation form to get x of k given k and p of k given k. Okay. So first you'll use this equation, right? You have this guy, you know this guy, you get x of hats. So first you get x hat of k minus 1, right? Then you cannot get this because you don't know this, right? So then you have to go into all the covariance matrices. So then you use update. Actually, it's not update, it's compute, because it's basically this computation. Compute p of k minus 1, because that uses this known stuff and known stuff, right? Then you use compute k of k using this equation, right? Should have numbered them, right? That's okay. And then compute. Now you can compute either this guy or this guy. So I'll just say both x hat k of k and p k of k. So p k of k is given by this equation, and x hat k of k is given by this equation. Right? So that's how you implement it. Yes.
So could you repeat why it is for in the Kalman filter, your Kalman gain is a function of k, but with LQE, your
so are you referring to the derivation that he showed you in 580? So he just does infinite horizon optimization there. We're just saying that over the infinite length of time, k is going to converge. Just going to pick the value which is converged. So we are optimizing over the entire trajectory. This is only optimizing at each step, right? So each step is going to be a different gain. But it also converges, because if you look at the Riccati equation, which I don't have right now, but it's basically combined, these two combined equations, P will converge as long as A, C satisfy certain properties. Observability, I think. Yeah, I'm pretty sure. Okay. A, C has to be observable. There are some conditions on A and Q also, I think. But if, yes, did you say yes? Okay. Okay, so yeah, A and Q also may need to satisfy certain properties. But P will converge and K will converge. And those are the ones that you usually use in the that LQE gain.
So conceivably, could you make your LQE gain a function of time?
Yeah. So LQE, so it's just Professor Bernstein does the infinite horizon case, and that's why you have, so really what's happening in that equation, you get P dot equals the Riccati equation, and you're setting P dot equals 0. You're saying that P is converged, P dot equals 0, the right hand side gives you a P, which gives you a K. But otherwise you'll have P dot equals something, and then K at each step is a function of P. So if P is changing, K is changing, right? Yeah, that's a good question. Yeah, a lot of these things are very, very similar, but different applications have different interpretations. This is exactly that observer. Okay, any more questions? Okay, so the last thing that I'll do is the UKF. So you'll probably have in the next homework you'll have something like this. We have a linear system or a nonlinear system, and you want to implement the one-step Kalman filter, two-step Kalman filter, and eventually you want to implement a UKF, right? So UKF. Does everyone know UKF? You know what it is? Unscented Kalman filter. Why is it unscented? Is this one scented? It was very sweet. Well, no one knows. So it's based on the idea of unscented transformations. And then I looked like, why is that transformation called unscented? Well, I didn't find anything. So I don't know. Okay, so UKF, I mean, it's a little difficult to explain because there is no analytical derivation for it. It's more like you look at the equations that you get with Kalman filter, and you look at how you can approximate them using ensembles and small ensembles. The thing with UKF is that it uses a very small ensemble. So other variation of Kalman filter is the ensemble Kalman filter, which instead of propagating the covariance matrix, it says that it's going to evolve an ensemble of states, and so you have like basically a bunch of samples, right? It's like sampling from a random variable, and you have a bunch of samples. Using those samples, you can approximate your mean and covariances. That's really what ensemble Kalman filter is, right? And UKF is saying that you can choose those ensembles in a much simpler way. So UKF is really an ensemble Kalman filter, but with a much smaller ensemble. So far you've seen that Kalman filter really is based on the idea that the underlying dynamics is linear, and the data assimilation step is linear, which makes the propagation of mean and covariance very easy, right? If you have random variable mu or random variable x, and you pass it through a linear system, then the shape of PDF doesn't change. It just shifts and stretches or something, right? So the error statistics are well behaved in a sense. That's why you get nice equations. But with nonlinear system, your statistics is going to completely change, right? If you have a squaring term in your system, your Gaussian PDF is already gone, right? You don't get the negative part. If you have random variable x, which is a Gaussian, which is a Gaussian or is normally distributed, if you square it, are you going to get -3? Now I'm going to get -3, right? So everything becomes positive. So right away, in the first step itself, your PDF is completely distorted. So that cannot be captured by the regular Kalman filter, right? So that's why we have the UKF, which instead of propagating covariance and mean through some analytical function, basically constructs an ensemble and passes it through the actual nonlinear system to compute the more approximate. More approximate is really not a technical term, right? Just a little better than what you had earlier. No one says that it's guaranteed to work, but most of the time it works. So more like if the ensemble Kalman filter is working with the same statistics, you can get the same performance using a smaller ensemble using UKF. It's more like that. Okay. So this is the reason I had to do the two-step, right? Because two-step, UKF is really approximating the two-step. Okay, 15 more minutes. Go 8. Okay. So these three equations. So let's look at these three equations. Gain K of K was, so P of K, K minus 1, C transpose. Okay. Now all the arguments that I'm going to give are basically hand wavy. Approximately they're true. So you just have to trust me. And P of K, K is P of K, K minus 1 minus K of K, C P of k, k minus 1. It should be a vertical bar. Right? So these are the two equations that we obtained using two-step Kalman filter. So if you look at this guy, and if you look at the beginning of your notes, if you made any notes, then you see that this is really the covariance of the output error, right? And I was writing covariance of z. This is what we got, like not the inverse part, this part, right? So this is the covariance of the output error. So we usually denote it by p by y, right? And this guy, so it's going to have, this is the expected value of E of k transpose, right? Something like that, E of k. Now what is E? E is the difference of states, right? So the first term is going to be like E, and the next term is going to be E transpose, and this is going to be C transpose, right? So what is this? This is Z, right? So that's like, this whole term is like the covariance of the state and the output. So that's going to be like P x y. It's more like P inverse, right? The whole thing becomes P inverse. Okay, is that convincing enough? Sufficiently? Okay. And the last thing is, yeah, I think that's the expression. Because we are going to approximate these values using the data now. So, okay, last thing that I wanted to say was, where did I get this question? Yeah. This, what is this like? This is like PYY, K of K transpose. How did I get this? It's just this expression. I push this on the left side, and I take a transpose. See, if I take a transpose of this, so let me just do that. That's going to be, this will come on the left, which is going to be PYY, K of K. No, it's yeah, post multiplying. So this should be PYY on this side. Yeah, but see, now I'm going to take the transpose because I have to get the C on the left, P on the right. P is symmetric. So that's why this comes on the left. Now, so this is like P, K, K minus 1, C transpose. Right? No. C, P, K, K minus 1. Right? So that's how you end up with, so K of K will look like something like Pxy, Pyy inverse. P of K is going to look like P of K, K minus 1. And then K of K minus K of K, Pyy, K of K transpose. So those are going to be the equations in UKF. Okay, 10 minutes. Okay, so now, so we assume that the real system is actually this, x of k plus 1 equals some function of x of k, u of k, and w of k, forget about that part. And y of k is g of x of k, u of k, right? I think it's the same thing, w of k plus v of k. But it doesn't really care about these statistics as much. Okay? So the goal is, we are given x hat k minus 1, and x and p k minus 1, k k minus 1. Find x hat k, k, and p, k, k. So that's what you have to do. Okay? So it's just a bunch of steps. And I don't even know how useful this is, but anyways, you have to use next 5 minutes. So you make, so UKF creates an ensemble. Those ensembles are called, that ensemble is called sigma points. So what it's going to do, it's going to find a bunch of points around your previous estimate based on your covariance, right? This covariance is saying like how is this guy distributed. So it's going to look at that distribution, it's going to pick up certain points in that distribution, then propagate those points. So you have, so let's say you pick up, so in a 2-dimensional space, it's going to pick up 5 points because it picks up 2n plus 1, where n is the length of the state. Okay? So it's going to pick up 5 states, 5 sigma points. It's going to pass them through the function f, all of them, and it's going to create, it's going to get these points, right? If this was Gaussian and your system was nonlinear, this is not going to be Gaussian. But if this was Gaussian, function is linear, this is going to be Gaussian, right? And then we use these 5 points to compute back the statistics of, so this would be like x k given k minus 1. This would be x hat k minus 1 given k minus 1, right? So that's your state estimates using the physics. So your physics equations are being used to propagate all these steps. And this is the only step which is different because the data assimilation step is always linear. Okay? So what you do is, so there are a bunch of papers you can see, but I'd like to write it like this. So what you do is you construct this big matrix x k minus 1. Okay? And you construct the sigma points like this, xk minus 1 given xk minus 1. So that's the first sigma point. Then you take this guy, xk minus 1, xk minus 1 plus eta times the square root of pk minus 1, k minus 1. Really fast. And then the third set is going to be xk minus 1, xk minus 1 minus eta root square root pk minus 1, k minus 1. Okay, so this is basically a big matrix of size n times 2n plus 1. Okay, so that's the square root of the covariance matrix, and this is a column. This is supposed to be a matrix, but it's more like this column is being added to every column of this matrix. So one column added to one matrix sort of means that you're adding that column to every matrix. So that's one of them, one column, n columns, right? So you get 2n plus 1 columns, right? Then you propagate this guy using the physics. So again, I'm going to write it, via notation, but you get the point, right? So each column is being separately propagated through the known function f, right? Oh, I didn't tell you what eta was. So these are like the tuning parameters. So you define lambda equals alpha square minus 1 times n, and eta is n plus lambda. Okay, so you choose alpha. That's the only thing you choose. Once you choose alpha, you have lambda, and you get eta. So that defines the spread of your sigma points, how far the sigma points are going to be chosen. Okay? And then the other thing that you choose is, no, don't choose, you define. W matrix vector is going to be like this. And this is 1 size 2 and cross 1. So the first one is lambda, and all the others are 1. And if you see, it's going to be 1. So these are the weights which we are going to use to collapse this ensemble. So this ensemble is, so this guy is also n times 2n plus 1, right? Okay. So once you have propagated your full ensemble, you want x of k minus 1. How would you get that? So this is the reason I like writing them in matrix forms. That's just this times w, right? That's this matrix n cross 2n plus 1 times this column vector, which is 2n plus 1 times 1, right? So you collapse the ensemble, and then you get a single point. Similarly, you're going to propagate the outputs. Y of k is going to be g x of k. That's the big matrix. So now you're going to get like a y matrix of your predicted outputs. Okay, let me erase this. And then you're going to again get y hat of k is simply equal to yk w. Right? So you make the ensemble, propagate through the nonlinear system, and you collapse it back. Okay? So that's your physics update. Okay? So that's like the mean has been propagated. Now you have to get the covariances. 4 more equations, okay? Just 1 minute. So we define x tilde at k as x of k minus x k minus 1. So what is that doing? That's subtracting the mean from your ensemble, right? So this is like your error matrix. And similarly, yk tilde is yk minus yk minus 1. Okay? And now you have to compute these guys, pxy, pyy, yeah, and p of k given k minus 1. So p of k given k minus 1 is just, so that's the error covariance of the state. So that's going to correspond to this matrix, right? So that's, it's easy to see that it's, I mean, I shouldn't say it's easy to see, but you look at it long enough, you'll see it. Right? So that's the error transpose error, right? Oh, I'm missing a transpose. And that's weighted by, so this WD is diag W. So if you do this in MATLAB, what happens? It creates a square matrix. Every entry is 0. The diagonal is W. Okay? So that's how you compute this guy. Similarly, you can guess how you would get PYY. That's just YK tilde WD YK transpose plus R. Right? So that's the covariance of this error. So this is an error, this is an error. And you sort of see how that expression evolves. And similarly, PXY. Guesses? No guesses? And you're done. Right? Now you have PYY, PXY, and this guy. Substitute back in this equation. You get P of K, given information till K, and the gain K. And then you use the same equation, which we used earlier, to update the state estimate. So that's going to be K minus 1, plus K times, the output error. Any questions? So we are at minus 3 minutes, yes.
This W is not the same as your process noise, is it?
What's that? Oh, yeah. So that's the big W. That's not the process noise. Yeah. Yeah, sorry about rushing through the end. Any questions? So I'll try to post all of this stuff in a much more understandable way on Canvas. Maybe like a couple days. Okay, that's it.